Yeah, thanks for the privilege and welcome to our next clips as we continue with our subtopics in elementary set theory. Now, in this clip, we're going to consider finite sets and cardinalities of finite sets. Finite sets and cardinalities of finite sets. Finite sets and cardinality of finite sets. This is what we are going to consider. Now, first of all, I want us to consider what finite sets are. Now, from our previous examples, I know that we are used to a collection of vowels, where we say let A be a collection of vowels, where we have A, E, I, O, U. I could remember that we have also talked about a collection, let B be a collection where its elements are even numbers less than equal to 8. Even numbers less than equal to 8 can be also a collection. And so on. We can also say it must not be that there must be an item. It's possible that a set might be empty. Like example, aged people or people on earth or in biospheric states, people in biospheric states that are of age 1000. Let's see be a set people of age 1000 in Yenagoa. Now this set, you know that nobody can live up to 1000 years. So it's obvious that there is nobody here, there is nothing here. So this set invariably will be empty set, which we sometimes denote as phi. Now, from these that we have given, let's consider another one, say D. Let it be a set X such that S is an integer where 9 is greater than X greater than 0. This can also be a set. Now, if you look at all these, you can see that all the elements that we have in set A are countable. There are things that we can count. How many elements are there in set A? 1, 2, 3, 4, 5. We can count them. They are countable. If you come to set B, you can see that a collection of even numbers less than equal to 8 is also countable. We can count the items. If you come to this set, you can see that yes, nothing is inside. So it's also known as countable. If you come to set D, we are talking about a set X such that X is an integer where it's within this interval 0 and 9, where we say 9 is greater than X, X is greater than 0. So the elements that we have in this set will be 1, 2, 3, 4, 5, 6, 7, 8. Because they said 9 is greater than x. So you can see that in this very set, these are the elements that we are expected to see. And in this set, they are also countable. So in other words, any set where its elements are countable is what we refer to as a finite set. So you talk about finite sets if its elements, if the sets in that particular element are countable. So here you can see that all these are countable. So these are good examples of what we refer to as a finite set. Now the next one I want to talk about is cardinality of a finite set. What do we mean by the word cardinality? Cardinality is simply means the size of the set. We are saying cardinality of a finite set. So now these are finite sets. Their cardinality is the size, or you say the modulus, and is denoted as this. This is how it's written. So if we want to talk about the cardinality of this finite set A, this is how it's written. The cardinality of A. And it simply means the size. What is the number? How many elements are there in set A? So this we can write as 1, 2, 3, 4, 5. The cardinality of A is 5. Of this finite set A is 5. If we want to determine the cardinality of set B, this we can also write as this. The cardinality or the magnitude, which is the same thing as the cardinality, is equal to how many? 1, 2, 3, 4. Is equal to 4. The cardinality of set B is 4. Like in this one, set C, people of age 1000 in Yenagua. There is no person that can live on earth up to 1000. So that set is 0, is empty. So the cardinality of that set C is 0. Whereas this one, the cardinality of D here, as we have highlighted here, is 8 if you count them. Numbers less than equal to this. Cardinality of this is equal to 8. So finite sets are the same thing as countable sets. Whereas their cardinality simply means the size, the magnitude of those, how many numbers are in a particular set. That's just the meaning. Now, it is also interesting for us to consider it in another way. Instead of counting, one can say, let's try to see if we can compare two sets. Let's try to see if we can compare two sets. If two sets can be compared. In doing that, let's say the magnitudes of A and the magnitude of B. Can we compare them to see if they have the same cardinality? Can we compare A and B if they are of the same cardinality? Now, they will be of the same cardinality if they have the same number of elements in them. Like in this case here, the cardinality of A is 5, whereas that of B is 4. So these two, they are not of the same cardinality. Now, instead of counting, we can write this as a pair. How do I mean? Like for A, we have A, E, I, O, U. This we can write as a pair as for A, you write A, and you take another one, mapping this one to this one, like matching them in this form, like matching them in that form. Matching them in this form, you can see that no one is matching you. So instead of always counting, you can just go ahead matching them, or we say mapping them. So this you can also write as a pair. This and this, this and this, this and this, E, 4, this, this, I, 6. We have 0, 8 in this case. But U is not marked. But the point I'm saying is, if A and B, assuming they have the same cardinality, you see that the pair will also be the same. Now, if we now assume that B is a set where its elements are even numbers less than equal to 10, in that you can now write U matching 10. U matching 10. So the point is, instead of just counting 1, 2, 3, 4 and like that, you can just write them as a pair. Or if you don't want to write it in this form, I can say these ones, I write them as A, E, I, O, U. This is set A. And I have another set here where I have 2, 4, 6, 8, 10. The way it's done here, you can also map them, linking this one, matching them. With this, you now know that these are of the same cardinality. Because you can see that the elements, the number of elements in A matches the number of elements in B. Now, at this point, I can give a definition where I will state that two finite sets are said to have the same cardinality. Two finite sets are said to have the same cardinality if and only if there is, if and only if there is a bisection. There is a bisection. This is another criteria to know if two sets, two finite sets, are of the same cardinality. Now, before I end this clip, I will want to just deviate a bit so that I can show why it must be in this form. Because I said they must have the same cardinality if there exists bisection. What do we really mean by that? What do we really mean by that. This will take me to introducing a concept called function. Let me quickly do that before I truncate the lectures. Now, we have said two finite sets are said to have the same cardinality. That is, if you compare the two sets, they are said to have the same cardinalities if and only if there is a bisection. Now, function. What is a function? A function is a mechanism or a system. Some people might say a mathematical construct. So as I was saying, I said a function can be seen as a mechanism or a system. Sometimes some say a mathematical construct that takes x values as an input value to itself and outputs y values or f of x values in a one-to-one correspondence. How do I mean? Let's consider a relation, a function, say f of x equal to say mx plus c. This is equation of a line. Or you can say, let's quickly say f of x equal to say 3x plus 2, where this is the point of intersection and this is our slope, where x is contained in this and this within this interval. Now, if this is true, we are saying that a function, this function here, it takes x values, one of these values, to itself. When you impute one of the values within this range into this expression, you will see that you have a value for f of x, which is the y value. That I said is a mathematical construct, it's a system or a mechanism that imputes, takes in x values to itself and outputs y value in a one-to-one correspondence. Now let's quickly go through this and see how this works. We have this. Here we have these numbers. We can say it can start from this because it's bounded here. 1, 0, 1, and 2. Now for the f of x, when x takes this number, this expression becomes 3 into negative 2 plus 2. This we have negative 6 plus 2 equals minus 4. So for this input value, f of x, f of this, where x takes this, becomes negative 4. When f of x takes negative 1, we have 3 into negative 1 plus 2. And this we have negative 3 plus 2 being equal to what? Negative 1. So when you take this, you will see that the corresponding number here is negative 1. Now for f of x equals 0, when is this? You see that we have 3 into 0 plus 2. This is 0 automatically, and we have 2. This becomes 2. For this input value, the output becomes 2. Now for f of 1, we have 3 into 1 plus 2. This one gives us 3 plus this gives us 5. For this, the corresponding value becomes 5. Now lastly, for f of 2, we have 3 into 2 plus 2. And this one gives us 6 plus 2, which is 8. So for this input value, we have a corresponding value, say 8. So you can see that we have said that a function is a system that takes in x values to itself, and as a result of what it has imputed to itself, it gives a corresponding y value, which are these that we have gotten. And as we stated earlier, we can also pair them with this same pair, this and this, this and this, this and this, this and this, this and this. So this kind of relation is called a one-to-one mapping. One-to-one mapping. And sometimes one-to-one mappings are also called injection function. Injective function. Injective function. Or you say one-to-one mapping. One-to-one function. So you can see that to every given input x value, for every input x value, we have a corresponding y value. And all of them, and there is no, in this system, you can see that no elements from the input value, no one element from the input value is mapped to 2 elements from the output value. Now, in course of these studies, these input values that we have is called the domain of the function. The domain of the function. Whereas the output values are called the range of the function. So these input values are also called the domain of this function, whereas the output values are the range values. So what I'm trying to say is that this kind of relation is called a one-to-one or an injective function. So for a function to be injective, we are saying that it must be one-to-one. It must be one-to-one. It must be one-to-one. No element from the domain must be mapped to any 2 elements from the range. Now the next one I want us to consider is, let's assume that we have a function, say 3, a domain variable 3, 2, and 1, being mapped to another one 4, 2, 0, and 5, where the mapping is of this form. In this case, you can see that in the domain, where this is the domain and this is the range, you can see that in the domain, all the elements here are mapped to the elements in the range. Now, for a function, for a relation to be called a function, all the domain element variables must be mapped out. domain elements in a one-to-one correspondence must be mapped out. All the domain elements. So in this case, all the domains here, all the domain elements are mapped out. So this one is called a function. Also in the first case that we have considered, all the domain variables are also mapped out. So this is also a function. Now, for it to be one-to-one or injective, it must be one-to-one correspondence. Now, in this case here now, you can see that all the domain variables are mapped out. Yes, but not all the range variables are mapped. But even in this case, this is also an injective mapping because all the domain variables are mapped to at least in a one-to-one correspondence, even if though one is left in the range. Now, if we choose to consider another example, say say 2, 3, 4 mapping to 2, 4, where this one comes to this one maps this one maps this. Now this kind of relation, is this a function? Yes, it's a function because all the domain variables are mapped out. But is this function an injective function? It's not injective because there is no one-to-one correspondence. You can see that two elements from the domain are mapped to one element. But I am here to tell us that this is a function, though not injective, but this kind of the formation we can say is surjective. Surjective in the sense that a surjective function is a function where all the range values are mapped. A surjective function is a function where all the range values are mapped. Surjective function. Surjective function or mapping. For surjective mapping, all the range values must be mapped. All the range values must be mapped for it to be a surjective mapping. But it's not injective. Not injective because we have two elements from the domain is mapping to one element from the range elements. But this is a surjective mapping because all the elements in the domain are mapped. Now, we have looked at a case where all the elements say 9, 6, 8, 7. Now, for it to be surjective, we have said all the elements in the range must be mapped. Now, in this case, you can see that this one maps this one maps this one maps this one maps this. Now, in terms of a function, this is a function because all the elements in the domain are mapped out. Now, this type of function, is it in the one-to-one or that is injective? Yes, it is because there is a one-to-one correspondence. All the domain variables are mapped to a unique value in the range. So this is injective. And is it surjective? Yes, it is also surjective because all the range values are also all mapped. So this is what I was saying. I said, and in terms of the cardinality that we were talking about, I said two finite sets are said to have the same cardinality if and only if there is a bisection. Now, these sets that we have here, and even in the first case that we considered, this set here, this mapping here, is injective and at the same time is bijective. Now, if a function, if a relation is injective, the same time bijective, that relation, that function is called a bijective function. If a function is injective and also surjective, then that function is called a bijective function. So you can now see that in this case, these ones are one-to-one mapping. They are all mapping to a corresponding unique values, and at the same time all the range values are also mapped. So they are injective, at the same time they are surjective. And we said if a function is injective and at the same time surjective, that function is a bijection. And from our earlier definition, if you can remember, we have stated that two cardinalities, two finite sets are said to have the same cardinalities if there exists a bisection. So this proves that definition that we have given. So conclusively, we have known what a finite set is. For a set to be finite, it simply means that the elements that are in that set must be countable. And the cardinality means the number of elements in that set